Right, here we go, Darren. This is a program on the grand unified theory, which is an attempt to put together or show the problems about putting together relativity and quantum mechanics.
Hello, Einstein left us with his theory of general relativity, which explained how gravity works on the scale of stars and galaxies and the universe itself. And Schrödinger left us with the equation that explained the mechanics of the tiny quantum realm. Both theories work to wonderful effect in their own worlds. But, and this is the sticking point, gravity is strangely absent from the quantum realm, and planets behave nothing like particles.
Right, I'd just like to stop it there straight away. So when it says gravity is strangely absent from the quantum realm, what that means is that gravity is so weak, it has no effect whatsoever on something the size of an atom.
Right, okay.
So if you wanted to measure the relative strength of, say, the electromagnetic force or the strong nuclear interaction and gravity, there would be a difference between them of something like 10 and 40 zeros.
Yeah.
So if you then imagine a book in your hand that you're reading, the whole earth is pulling that book down, and you can easily hold it up. Now that takes something the size of the whole earth. So imagine if it was only the size of one atom compared to the whole earth, how weak it would be.
Right.
So it's not that it's absent, it's that it has no effect. So that's very, very different. So let's get back to the program.
The enigma for scientists throughout most of the last century is that, as they're currently formulated, general relativity and quantum mechanics cannot both be right.
Now again, as they're currently formulated, they cannot both be right. But we know from experiment that they are both right.
Yes.
So as they're currently formulated, if you translate that to how we interpret them, that's a completely different question.
The history of 20th century physics has been a struggle to find a way to unite them, to find what has become the holy grail of modern physics, the grand unified theory. With me to discuss the dilemma of modern physics and the quest for its solution is Brian Greene, Professor of Mathematics and Physics at Columbia University and author of The Elegant Universe, Superstrings, Hidden Dimensions and the Quest for the Ultimate Theory. I'm also joined by the Astronomer Royal, Professor Sir Martin Rees, whose work Just Six Numbers also tackles this problem. Brian Greene, can we begin by explaining why Einstein's theory of general relativity can't be incorporated into the current understanding of quantum mechanics?
Sure. The basic idea in Einstein's theory of gravity general relativity, strangely enough, is that the fabric of space itself is connected with the force of gravity. It's kind of a hard idea to imagine, but it's as though the
fabric of space, excuse me, that's an oxymoron.
Right.
Fabric has physical properties, space has none.
Right, okay.
So we're thinking about something wrongly.
fabric of space bends and warps, and in that way communicates gravity. The only thing we need to know, though, is that the curves in space from his theory are viewed as gentle curving geometry. But at the other end of...
Now, please notice, he just used the word geometry. Gentle curving geometry.
Right, okay.
Quantum mechanics behaves as units, like arithmetic. Mathematical ideas being introduced into physics. That's going to be very important later.
The spectrum in the quantum realm, we learn that microscopically the universe is a jittery, frenzied, turbulent arena, very different from the gentleness of Einstein's theory. And it's that jitteriness of quantum theory versus the gentleness of general relativity which makes it so hard to unite them together.
In your first sentence, you said the fabric of the universe. Could you tell people what you mean by the fabric of the universe? I don't know.
Sure, it's one of the more elusive ideas of modern physics, but it's a very powerful one. It's as if we are all immersed within an environment, the fabric of space. It's the stuff around us. You can't really grab it or hold on.
So it's just said the fabric of space is the stuff around us. That doesn't make any sense.
Right.
It's non-physical. But as we've seen in the previous videos, if you move over to the mathematical universe, it's not a problem. Because underneath all of physical matter, there are only quarks, leptons, magnetic fields, which have no physical part to them. It's all
Right.
mathematical. The physical reality can emerge out of purely mathematical properties.
Right. Okay.
So that's why he can't explain it, because he's trying to explain space in physical terms and he can't do it. He can explain it in mathematical terms. That's no problem.
Right.
To it, but you can feel it. Because right now, each of us is being pulled by gravity. We feel that, each of one of us. And according to Einstein, it's warps in the fabric of space, which cause us to feel gravity. So you, me, everybody else right now, we are sliding down an indentation in the fabric of space caused by the presence of the Earth. We are all moving, in a sense, under that force right now.
So let's just put that into proper language. If you state that matter, the Earth, and space are obeying mathematical rules, that's not a problem.
Mm.
So you don't need a physical explanation for everything, because there isn't one. It's a relationship between the physical, the Earth, and the non-physical space.
Right. Okay.
And you can explain both of those in purely mathematical terms.
And why is that so distinctive from quantum mechanics? Why is that relationship so far away from the way in which you understand the world at the tiniest level? One would presume that from the tiniest comes the greatest, from the small comes the big, from the detail comes the general, and so on. But what you're saying, I mean, my goodness, am I being banal? Never mind, here we go. What you're saying is, right, there's this huge theory which gently warps the fabric of the universe, and then it is built on the particles, the quarks, nothing at the bottom, which a theory which has got nothing to do with the huge theory. And so, ordinary Joes would say, well, why don't the building blocks lead to the building?
Well, that's exactly what's been motivating us for 50 years. We hold that same intuition that the big stuff should be built up from the small stuff, and therefore the two theories that have been developed of the small stuff quantum theory and the big stuff general relativity should fit together. They should.
So if we can now distinguish in the mathematical universe the difference between the non-physical stuff, which is underneath, and then the physical stuff, which is above, and there's two different sets of rules, that's no problem under a mathematical universe, because you can have two different sets of mathematics. You can't explain them both with one set of physics, which you're trying to do. You can explain them both with two different sets of mathematics, which are compatible.
Okay.
So you've done it. You've escaped from the tyranny of tradition.
Okay. And what are the two different sets of mathematics? The two different.
Well, there's layers and layers and layers, but the base set of mathematics is the fact that in quanta, things are countable. You can count quanta.
Yeah.
Now, you can't count a gravitational field. You can just say that it bends geometrically. But you can count the Earth. But the Earth doesn't come in an exact unit, which is all the same. So every electron, all the electrons are identical. All the mathematical units are the same. But it's not a unit of substance. You can say a unit of energy, but that's not a physical thing.
Right.
So if we stop thinking that down there there's physical, so there's one set of rules for the non-physical, and then another set of rules, the Newtonian rules, for the physical. Now it's no problem.
Right.
Could smoothly move from one to the other, but as they're currently formatted, they don't do that. That's been the driving force. Now, why don't they fit together? Well, we think it's because when you formulate quantum theory, it's a very different language. It's a very different philosophical orientation to how the universe is put together. And that has been part of what we need to overcome in stitching these two theories together.
But when we talk about missing physics, we mean we've got the little, we've got the big, we need something in between to link them together.
We need a bridge between them.
Martin Rees, how do you see that?
Well, we do need the bridge, but we've got on fairly well in most of science without the bridge. And the reason for that is that normally we don't have to worry about quantum theory, that's the microphysics, and gravity at the same time. In the case of ordinary atoms and molecules, we have to worry about all the counterintuitive effects that we've learnt about since the 1920s, called quantum theory. But on the scale of single atoms, gravity is quite unimportant. On the other hand, when we get to the astronomical realm, the Earth, planets, stars, etc., gravity is the dominant force. It's what's holding us down on the Earth. But in large objects like planets, gravity is dominant, and the counterintuitive features of the micro world, the fact that on the very small scale we can't localize things, we have this intrinsic uncertainty, those effects are not important.
So they just said that the atomic forces are not important, but he's fallen into a trap.
Right.
The sun doesn't stay up unless what's happening at the atomic level holds it up.
Right.
So the release of energy from nuclear interactions is the only thing holding the sun up against its own gravity. So the sun is a relationship between the big and the small.
Right.
So think of a balloon, the skin of the balloon pulling in, the pressure of the molecules not wanting to go together at the atomic level hold the balloon up.
Right.
But because the atomic parts are non-physical, if you can squash them together, you just get a black hole. And all physicality disappears.
Right.
So what he hasn't explained there is that a sun or a star is a relationship between gravity and the strong nuclear interactions. A planet is a relationship between gravity and the electromagnetic interactions, which is the only thing that's holding the Earth up against its own gravity. And that's the difference between a star and a planet. So that's cleared that one up.
Mm.
They're both relationships between what's happening at the small level and what's happening at the big level.
Right.
And if that relationship isn't there, you don't get a star or a planet, you just get a black hole. In both cases. So that has to be cleared up once and for all.
On something as big as a planet, and therefore it's only in extreme situations that we actually need to confront this unification, and those extreme situations come first of all right at the beginning of the universe, when we believe everything in the universe was squeezed to the size of an atom, as it were. So we clearly have to worry then about gravity, and so we won't understand the real beginning of the universe until we have a theory that can cope with both gravity and quantum theory. And also there are other exotic situations, and of course, as Brian Greene said, we won't understand really what space is like unless we can understand its structure and why it has the effect of transmitting gravitational forces, as it were.
Don't you find it intellectually annoying, though, to put it at its very slightest, that these two things can't be connected? I mean, in your work, you find yourself able to do your work without any reference, with one theory without any reference at all to the other? You don't think that perhaps the other might be having some effect that you haven't yet, don't want to say it, imagined or thought?
Well, certainly we'll get a deeper insight when we have this complete theory, but I think it's important to realise that most of science gets along on the basis of its set of concepts that don't involve all these deep mysteries. Ordinary atomic physics and chemistry and certainly biology proceed independent of all this, so it's only some kinds of science which actually...
So there, when he said biology gets on without this,
Yes.
now that's a real problem, because biology is the same matter that makes a star and a planet.
Mm.
So that's a big problem. Now,
Yeah.
if we go back over to the mathematical universe and state that biology is another set of mathematical laws on top of quantum theory, classical theory, chaos theory, complexity theory, and then you get chemistry, and then you get genetics, then you get biology, it's not a problem. They're all mathematical. They're all mathematically driven. Mathematics is causality, because biology has no forces in the classical sense that make it work. Neither does chaos or quantum mechanics or complexity or human behavior. And Einstein's already thrown out gravity as a force, so now you're in real trouble.
Right.
Gravity is the geometric or mathematical description of space and matter.
Right.
Completely and utterly different. And you cannot explain a star as anything else but the relationship of what's happening at the atomic scale in a partnership with what's happening at the gravitational scale. It's both at the same time, and they can't see it.
Depend
Right.
on having these new theories, but conceptually, of course, these theories are crucially important because, in a sense, they would be the next step in the quest to understand the basic stuff the world is made of that goes back to the Greeks. We have understood for at least this century that everything is made of atoms. We now understand the structure inside those atoms, but the next step, of course, is to try and unify all the forces, to connect the forces that govern the microworld of atoms. These are the forces of electricity, the forces that hold atomic nuclei together, which we do understand to some extent, and to link those with the force of gravity, which is what we feel here on Earth.
So the new way of looking at things says that gravity must be utterly and completely different from the atomic forces, otherwise they don't work together, they don't make stars. The difference between things makes them work together.
Right.
And that is the challenge which Brown-Green is addressing.
I'm coming back to Brown-Green in one moment, but as I understand it, Heisenberg's uncertainty principle is one of the most profound aspects of quantum mechanics. Now, can you just say how it affects quantum mechanics and why it has no place in the work you're doing in astronomy?
Oh, it has a very big place in my world because the whole nature of atoms depends crucially on the fact that atoms don't obey the ordinary billiard ball equations that Newton taught us, and to understand everything about atoms and how they stick together to make molecules, planets and stars, we certainly need to incorporate quantum theory, and indeed most of 20th century science and technology depends on the fact that on the scale of atoms everything behaves in this very spooky way, as it were, where you can't say simultaneously exactly where an electron is and exactly how it's moving.
I expressed myself badly because what I meant to say was that what we know about that, does that affect your work on positioning the planets, for instance?
Well,
That's an important thing to pick up, because positioning the planets, you're in the physical world, where things behave as physical objects. Underneath that, things don't behave as physical objects. And it's trying to describe them both with one set of laws, which is the problem. You need two different sets of laws to get a star or a planet.
Right.
So you've got to have these different sets of laws for everything to work.
when we are talking about the gross features of the universe, the planets and the stars, etc., then we are concerned with gravity. And Einstein's theory of gravity is good enough for all these situations. The planets and the stars move in their courses through space according to the laws of Einstein's theory, which in fact in these contexts aren't too different from what Newton taught us 300 years ago. And because the planets are so big, the sort of jitter or fuzziness in their positions, which stems from the Heisenberg uncertainty principle, is trivially small, because the bigger an object is, the more firmly localized it is. So it's only when you get down to the very small that you have to worry about this fuzziness, or, in the case of the universe, when you get back to the incredibly high densities which prevailed at the beginning, when the entire universe, as it were, was squeezed so small that a quantum fluctuation could shake the whole thing.
So we've reiterated that what you said at the beginning, that you can effectively get on with the work you're doing with one theory and without the other. Brian Greene, more than once Martin Rees has pointed us towards the Big Bang, which as being both massive and tiny, supposedly going to tell us containing all matter in the universe, yet compressed into something incredibly small. Is it calculations in this field that are the driving force behind the quest for the grand unified theory?
Certainly. The deepest questions that a unified theory such as string theory faces is trying to describe extreme realms of the universe where you need both the laws of gravity and the laws of quantum theory. And those are realms that are huge and heavy, but also tiny from the point of view of size. So the Big Bang, when everything in the universe was crushed together to incredibly small size, it's heavy, but it's small. Black holes, another realm where a lot of material is crushed to incredibly small size. Again, it's very massive, but very tiny. Those are the realms where these unified theories come into play, because you need the ideas of both quantum theory and gravity, namely general relativity.
So what do you know about the Big Bang in terms that would make sense to me, and I hope to people listening that gives you hope that these two theories will come together? You've described it in general terms. What more particularly?
Well, the Big Bang is an area of very active research today, and string theory by no means has resolved many of the puzzles surrounding the Big Bang. But black holes, the other example I gave, perhaps better illustrates some of the power of these ideas, because in the last few years, string theory has been able to resolve an idea that was initially put forward by Stephen Hawking in the 1970s having to do with black holes. He discovered an interesting fact. Black holes, it turns out, embody a certain amount of disorder, or the more technical term is entropy. But nobody could figure out where the disorder in a black hole came from. Finally, string theory, using the new ideas of the last few years, has been able to very accurately describe where the disorder in a black hole is and came out with a numerical answer that agrees exactly with what Stephen Hawking had predicted. So it's a very powerful confirmation that these ideas are making contact with real physics.
Could you tell us, is it possible to tell us, I mean, some things aren't possible to say in a conversation, but is it possible to tell us what string theory is?
Sure. I think the basic idea of string theory can be described quickly in a nutshell. As Martin Rees was saying, we have for thousands of years asked a simple question: what is the stuff of the universe made of? Namely, if you take any piece of material, wood, iron, anything, slice it in half, slice that piece in half again, and keep on cutting, what's the smallest ingredient that you'll come upon?
So here's the old way of looking at things. If you take a piece of material and you cut it into small pieces, the old way of looking at it is that you get some very, very small pieces of material. The new way of looking at it is there's no material, there's no physical presence at all to the electrons and quarks, which makes the material, because they don't need physical properties to make physical material.
Only mathematical properties?
Only mathematical properties. That's all we need.
Okay.
And indeed, in our century, we've learned about atoms, but we know atoms are not the end of the line because they're made of smaller things. They can be split. They have little electrons that swarm around a central nucleus, and it can be split because the nucleus itself has neutrons and protons. And they're not the end of the line either. It's somewhat like a sequence of Russian dolls. Inside neutrons and protons are smaller particles, discovered in the late 60s, known as quarks. What string theory does, it comes along and says there's one more layer of structure. Deep inside an electron, deep inside a quark, deep inside any particle, in fact, is a little tiny loop of energy. It's a little filament of energy vibrating to and fro. And the key idea is that just like the string on a cello or a violin can vibrate in different patterns, which our ears sense as different musical notes, the little strings in string theory also can vibrate in different patterns, but we don't hear them as different notes. Rather, we see them as the different particles in the world around us. So using the metaphor, an electron is a string vibrating like an A sharp, or a quark is like a string vibrating as a C flat, or something of that sort. So that is the way in which we can think of all of the rich material in the world around us being generated from one fundamental vibrating ingredient.
So notice that he said energy. The string is just energy. So that's non-physical. So at some point, you've got to state that things become non-physical. Now, there will be a point at which we can say that's a physical something.
Okay.
Now, that hasn't been established by science.
Right, okay.
So that something stops behaving to quantum rules and can only behave to classical rules. That's where the join will be. But that's not been established as yet.
Ah, right.
How do you see, know, understand, how do you get your hands on that one vital ingredient? Can you see it? Or is it an active imagination?
At the moment, it's an active theorizing, so it's imagination, but bolstered by the quantitative ideas that we're able to develop surrounding the idea. But the reason we can't see it yet is because the strings are really tiny. So just to give you a sense, they're about, well, numerically a billionth the size of an atom, so they're tiny. But an analogy, I think, gets the idea across better. If you were to take, say, a single atom and magnify it to be as big as the entire known universe, then a little string in string theory would magnify roughly to the size of an average building of maybe 10 stories. So a 10-story building is to the entire universe as a little string is to an atom. So that's why they're so difficult to see directly, because it's way beyond our technology to see something that small.
But you're absolutely sure they're there, are you?
Absolutely sure? Certainly not. We won't be absolutely certain until there's experimental proof of these ideas. But the last 10, 15 years have convinced us that this theory can solve problems which could not be addressed in any other method. And just going back to the somewhat philosophical side, I think each of us, I think, has a gut sense that the universe cannot really be described by a patchwork of two good theories, each of which is incompatible with the other. The universe exists, it's a single place, there should be a single consistent theory describing it all. And that's...
Now that is absolutely true.
Yes.
There must be a single consistent theory describing it all. Now, if mathematics describes quantum mechanics, classical physics, chaos theory, complexity theory, genetics, chemistry, biology, human social behavior, economics, then we already have a theory, but we haven't recognized it.
Yes.
So that's the problem, is that we don't recognize something which is not based on tradition.
Right, okay.
So the pull of the status quo and tradition is all powerful to the brain because it goes for them first. New ideas, just so difficult for people to accept, but the younger generation who haven't made their mind up will make up their own minds. So that's what's coming.
Yeah.
When you give the younger generation what he's just asked for, a logical explanation for the whole of nature that's self-consistent, they will make up their own minds as whether they want to use it or not.
Really what's driven us to try to construct that unified theory.
Magnus, Einstein tried to solve this puzzle, didn't he? Why did he not succeed?
Well, Einstein was really trying to do it prematurely. He didn't know enough about all the forces that needed to be incorporated, so his efforts were doomed to failure. But he obviously was striving for what Brian Greene's colleagues are still striving for. And I think the interesting question is, what are the prospects of succeeding? Because, first of all, as Brian Greene said, the scale of these strings is far, far smaller than we can directly measure. And also they involve very, very complicated geometry, not just 3 dimensions, but 10 or 11 dimensions. And so, first of all, they involve mathematics, which for the first time is challenging mathematicians. I mean, Einstein used maths that was on the shelf already from the 19th century. So did the pioneers of quantum theory. But the mathematics needed for superstring theory is still challenging mathematicians, so we've got to learn more mathematics. It's the first time in science we've needed more mathematics to make a scientific breakthrough. But the other point is...
Really, the first time ever?
Well, maybe not quite the first time, but if we think of the great advances in science, they've normally used maths which to pucker mathematicians is fairly old-fashioned and standard, whereas that's certainly not the case for what they're thinking about in superstrings. But the other issue really is, how will we test it right? Because we can't directly probe these strings. We will hope that one can understand well enough.
The math, what they're saying there about maths and stuff, the greater maths needs to be discovered. Well, it doesn't though, does it? The maths is already there that can explain these theories.
It is. But if you haven't recognised the mathematics as causality, you're saying that physics is causality because it has forces, then you're in trouble, because physics doesn't have any forces because Einstein's already thrown out one, gravity.
Right.
Therefore, you've got to throw out all the others. And quantum mechanics has never had any forces. Chaos has never had any forces. Biology has never had any forces. Chemistry has never had any forces. So you're looking at it wrongly.
Yeah.
So it's all mathematics. So that, again, you can see the problem with tradition, just warping the mind.
Mm.
The theory that you can actually calculate something about ordinary atoms, ordinary electrons, etc., and the ordinary forces, which we can perhaps test. And just to highlight the limitations of present knowledge of the microworld, we know there are atoms and electrons, etc. We know about different forces, but we don't know why they have those particular strengths. We don't know why an electron weighs 1,800 times less than a proton and things like that. And if this superstring theory succeeded in explaining some numbers that we can't yet predict, then of course it would gain credibility. So we don't actually have to observe this tiny scale. We need to be able to calculate from it something we can directly observe so that it gives a number which we can compare with observation. And then there's another thing which interests me very much in a more philosophical way, and this relates to my book Just Six Numbers, which addresses the apparent special nature of the laws in our universe. And the question there, and I'd like to know what Brian Greene thinks about this, is whether this ultimate theory will lead to a unique set of laws of nature in our low-energy world, or could it be that a Big Bang cooled down and ended up with a quite different physics, different numbers of dimensions, different kinds of atoms in it, etc.? Because if that's the case, it will mean that we can think of our universe in a different context, and in a sense cosmology will become rather like biology, in the sense that we won't be able to explain directly the physics we see, because it may be some sort of historical accident of how our particular Big Bang behaved. And so I think it's very interesting to know whether we will ever have this theory worked out enough, whether our brains can cope with the mathematics, and also what consequences it will have in the everyday world.
Well, I hope that string theory ultimately will give a unique prediction for how our universe is, and that prediction agrees with what we actually see in the world around us. Because as you say, there are a bunch of numbers that people have measured fastidiously over many years, some of which you've mentioned, the mass of the electron, the mass of quarks, and the strengths of the forces and so forth. But nobody can explain the numbers that the experimenters get. And it's not just a question of idle philosophizing, because it turns out if those numbers had been even a little bit different, a few percent different, the universe as we know it would not exist. It would go away. Stars, for instance, rely upon nuclear processes, which themselves require delicate interrelations.
So what he's just said there, stars rely on nuclear processes. So he's put together what's happening in the atomic world and related it to the gravitational world.
Right, okay.
Each one doesn't work without the other. If the star doesn't have lots of gravity, it doesn't push protons together and generate new elements which hold the star up.
Right, okay.
So it's that relationship which is important, not one or the other.
Right.
Look at the relationship, don't look at it's both and, not either or.
Between these numbers, these particle masses and so forth, and if you change those numbers, the nuclear processes go away, stars don't light up, and without stars the universe is just a very different place. So I think perhaps the deepest question that science faces is, why is it that those numbers have just the right values to allow stars to exist and planets to form, and at least on one planet, life to actually exist? So we hope that string theory will come to a unique answer, but we don't know as yet. We don't know enough about the theory to know if it will do that.
In passing, Martin mentioned working in more than 3 dimensions. Einstein suggested time as the 4th dimension, but you're up to 9, 10, 11 dimensions. I just cannot, I've got no purchase on that. Can you try to give us some idea of what you're talking about there?
Sure. One remarkable feature of string theory is that it only seems to make sense. Internal consistency of the theory seems to demand that the universe have at least 6 and probably 7 more space dimensions than we're directly aware of. So, first of all, what does that mean? Well, we all live in a universe where we freely move through 3 dimensions all the time. Left, right, back, forth, up, down. 3 independent.
Now just listen to what he said. We all move through 3 dimensions, back, forth, left, right, up and down. That was 6.
Yeah, exactly.
And if they're mathematical dimensions, you don't need to be limited to 3 physical dimensions. You flipped over into the world of mathematics. But he did just say 6.
He did, yeah.
He did. So if you're outside a box, there's 3 physical dimensions. If you have a brain and you're in the middle of a box, then there's 6 mathematical dimensions. There's no other way to explain the difference between left and right.
No.
None whatsoever. So if science can't explain the difference between left and right, it's not really credible.
Directions. Include time, as you mentioned, that takes you to 4. We're saying that there are 6 more, probably 7 more space dimensions beyond the ones that we know about. How do you think of that? Well, I think an analogy helps get the idea across. If you imagine in your mind's eye, say, a big, long piece of a garden hose that you stretch out between two posts in a field, and you walk maybe a half a mile away from that garden hose and you look back on it, well, it's going to look like a one-dimensional line, excuse me, because you can't actually see the thickness of the garden hose from a distant vantage point. So if a little ant were living out its life on the hose, you'd say, well, it can move in the left-right dimension, but that's it. Only one direction in which it can move on the surface of the hose. But then if you take a pair of binoculars, for example, you zoom in on the garden hose, you now see that it has thickness. You now see, in fact, there's a second dimension, a dimension that's curled around the surface of the garden hose. So the little ant can not only walk in the left-right direction, it can also move counterclockwise or clockwise, a new direction that you only know about if you can zoom.
So again, he said clockwise or counterclockwise, a new direction. That's two directions, surely.
Mm. Yeah.
So you can see all these mistakes, and once you've got the answer, you can correct them. Logic.
Yeah.
Zoom in and really magnify the object that you're looking at. Well, we think the universe may be very similar to that. There are three big, obvious space dimensions, like the unfurled extent of the garden hose, but there may be others, perhaps 7, more curled-up dimensions, like the circular girth of the garden hose. But we think that perhaps they're so tiny that as yet nobody has the equipment necessary to magnify them to a scale that we can actually see. And that's how we make sense of this rather strange prediction that there are more dimensions than meet the eye.
Why do you choose 7, and why are they significant?
Well, when you study the mathematics of string theory, it turns out that there are equations that demand that particular number. Basically, there's roughly an equation that says, unless there's 7 more dimensions, this theory falls apart. So we pick that number in order that the theory makes sense, and then we go forward and see what else it has to say about the universe.
Is this entirely speculative, imaginative? I mean, what empirical evidence is being brought to bear on this at all? Is this just mathematicians having fun? Is this angels dancing on the head of a needle?
I don't think so. I don't think it's angels dancing on the head of a pin, because we do believe that general relativity describes gravity because experiments have shown it. We do believe that quantum mechanics describes the microscopic realm because experiments have shown that. We also feel that there should be one theory that puts them together in a consistent package. And string theory is a theory which does that. So there is experimental support for the two underlying structures of the theory, and then we have to see what that union, that consistent union, tells us. And one strange fact is it seems to tell us that there are more dimensions. But let me just add to that. There is an experiment that's going to be carried out in the next couple of years in the United States at Stanford University and in Colorado, where experimenters are going to try to search for signatures of the extra dimensions by very, very accurate measurements of gravity on tiny sub-millimeter scales. So it's a long-shot experiment, but it's possible that with those experiments they will get indirect evidence for the existence of these extra dimensions. And if those experiments are positive, I think it's going to be one of the most dramatic discoveries of all time.
Why? Martin Rees, why do you think that'll be the most dramatic discoveries of all time?
Well, it'll certainly, if it works, be telling us something new about the fundamental nature of space and time, and being at least a step towards unification. It will indicate that Brown-Green's theory is on the right lines. And, of course, that will increase the chance that perhaps we will, one day this century perhaps, have this theory that will explain the basic forces of nature. But I think it's very important for physicists, when they talk about this, to emphasize that this is just one branch of physics, and physics is just one science. And I think we have to be modest and realize that for most of the rest of science, this theory is going to be entirely irrelevant. And let me give...
So I'll just say that again. For most of the rest of science, this theory is going to be entirely irrelevant.
Yeah.
That's not very useful to you, because you haven't explained a snowflake, a solar system, or a snail.
Yeah.
Entirely irrelevant. So maybe you're on the wrong track.
Yeah. It's
That's
damning, isn't it? It's a damning line.
Yes, it is. Yeah, entirely irrelevant.
An analogy here. My favourite analogy is with a game of chess. If you imagine watching people playing chess, then eventually you could figure out what the rules were. But of course what makes chess interesting is not the rules, but the enormous complications that they allow in the play. And what we are doing in physics is to try to understand the basic rules that govern nature. But just as in chess, simple rules, 64 squares on the board, 6 types of pieces, allows immense complication, So when we've got these rules playing out in our vast cosmos, then of course what they allow is all the complexity of the everyday world and the astronomical world and all the complexity. And so it is that which is the unending quest for science. And another way to put this is that in the case of science we can highlight three frontiers: the very big, the very small and the very complicated.
So let's just stop them there. The very big, the very small and the very complicated. Now that's nailed it. The very big, you've got general relativity.
Yeah.
A mathematical description of matter and space. The very small, you've got quantum mechanics and classical mechanics because you still have electromagnetic fields. That's very important. But it's quantized, so it's arithmetic. So it's, again, it's a mathematical description of what happens at the atom. And then you've got the very complicated. Now that's very important because physics doesn't lead to complexity. It only leads to uniformity. So the physicists are never going to explain complexity.
No.
The mathematicians can. That's already been done. They're well on the way with that. So you've already got the answer. You've got the very big, you've got the very small, and you've also got the very complicated, but you can't see it.
What we're trying to do is to unify the very big and the very small. That's what superstring theory may do. But the greatest frontier of all, which most of science is concerned with, is the very complicated, and that is the unending challenge of science.
And you don't think string theory will necessarily address that?
Well, I think it won't be relevant to that because if you're a biologist or a chemist, you don't really care about what's happening inside an atom. And you care still less about what's happening on scales a billion times smaller than an atom. And so it deepens our insight. It's of great philosophical importance to all of science, but I think Brian Greene would agree that to the practitioners of most sciences, it's a philosophical interest, but it doesn't affect the work they do, because we can't actually do a calculation from this level for a single atom, certainly not for anything complicated.
But to come back to where we started, Brian Greene, the grand unified theory, the theory of everything, there's an expectation in those very phrases that there'll be Shazam, boom, all will be solved, and the Big Bang will be solved, and by having a theory of everything, by uniting these two theories, we will know in a fundamental way which will permeate everything else that we know.
It's an unfortunate name, in my opinion.
Well, do you think that that's so?
Well, I think, as we discussed before, that string theory may well one day give us an explanation for the Big Bang, how the universe began and how it evolved from its state way back then, maybe 15 billion years ago, to the form we witness on a dark, starry night. But it's certainly the case as well that we are limited in our ability to go from the fundamental rules, as Martin Rees was saying, to understand the most complex things around us, the brain, for instance, psychology.
So there is saying again that physics explains uniformity, a raindrop, a sphere, is uniform. But what about the snowflake? Now, most people think the snowflake is all sorted out by physics. But if they read Frank Close's book, The Cosmic Onion, he states very clearly why the laws of physics do not explain the shapes in snowflakes. He states it. He states that the underlying laws of physics show no prejudice to stick together in one direction over another. That's it. So it's the very complicated, or any complexity at all, which the physicists have to give up on trying to solve themselves. Physics explains uniformity. Chemistry and biology play out on the stage of physics. It's just the stage. That's all it is. You can't have the play without the stage.
Yeah, so
that's okay.
So physics is the basis then?
Yes.
Right,
the first set of laws that let everything else take place.
Right, okay.
So my bones behave to the laws of physics. They can also evolve the laws of biology into a human hand, a bat's wing, or a whale's flipper.
Yeah.
At the same time as obeying the laws of physics still.
Yeah.
So you can do both.
I don't think anyone's ever going to understand depression from the point of view of string theory. But we will understand other more simple questions, such as how the universe began, how a black hole exists, what it's like to be at the center of a black hole. Those, it turns out, are far simpler questions than understanding a question like depression, because we're talking about the fundamental structure of our universe. And that, I think, is a compelling kind of question to try to address.
Mind you, I mean, I'm treading very, very carefully here with you two, but it has been proved true again and again over the last few hundred years that you don't know what the outcome of these discoveries are. I mean, Newton's laws of motion led to things that he could not have imagined, and so on.
Yes, absolutely. One always has to bear in mind that discoveries which seem abstract and esoteric today can sometimes have important implications for things in the future. So could well be the case with string theory as well.
Thank you very much, Brian Greene. Excellent book, The Elegant Universe. Martin Rees, excellent book, Just Six Numbers. And thank you very much for listening.